Hey, I'm Youjiang Shen, and today I'm going to introduce a satellite-based advanced reservoir operation model and SPTS. So we know that globally there are many reservoirs built worldwide in global rivers, and here we found that according to the most recent GDW dataset, it's about 31,000 dams with a special information mapped on the global rivers, and 7% are designed for flood control, which particularly impacts the natural flow regions. And actually in reality, their operations are very complex. They have to balance different purpose, and also they are involved with the regional variability and operational nonsense by the human beings. And how much water they are released to the downstream are actually very difficult to model because there are few reservoirs available with the operational data. So previous models from the first generation, a simple water access model, to more complex genetic models, like including their main use, water demand, and operational bounds like Hanasaki. They are relied on assumed reservoir behaviors, actually, but they are not generalizable and inadequate across reservoirs. And here we aim to advance reservoir operations in our satellite era. And my solution is to incorporate in satellite observations to develop a model. The core idea is that can we use satellite observations to model reservoir operations for global reservoirs? And here I proposed a satellite-based target storage model, SPTS. And the first one, it typically divided reservoirs into different water zones. And for each zone, we established the release and the storage relationship. And these zones use generic zoning and derived using machine learning. And then piecewise linear equations are formed to model the water release in each zone. And the second rationale behind it is that we know that satellites can see the storage variations, and this is the monthly seasonal targets patterns. And I use this dynamic monthly target storage in the past, and I assume that the reservoirs typically operated with seasonal targets, and these are implicitly captured in the historical storage times. So I set this as a target in the operating roles, and the release are then adjusted based on the current status of the water and the regulation capacity, and the monthly median storage are used as a target. So the goal is I developed SPTS, trying to make it smarter to learn from the past. And this is also the first attempt to using satellite observations to develop a model. And how good it is. So I tested its performance across global reservoirs. The first one is local experiment. I tested the operation models, like 3 models, and against our SPTS, and across 289 reservoirs globally with observed inflow to drive this, and to test how good it is in simulating outflow and storage. And here is KGE values. And you can see overall, it achieves a median KGE value for store outflow about 0.5, and for storage 0.17, and it's good comparing to the others. And if we look at it more specifically, we found that for large one and cold one, and those reservoirs are intensively regulated, it have a better performance. And I guess it is reasonable because for those, they have more irregular inflow patterns, and and here is a more specific example to illustrate why it performs good. And this is, you can see, this is a stream introduced snow like floods in spring seasons. And this is a stream inflow patterns. And here is our target storage. And this is our satellites captures well with observations. And here is the previous models using the very simple method, linear interpreted. And you can see like with this inaccurate target, it will have like a result like inaccurate storage. But our, see the purple one, it can capture the inter and interannual variability very well. So it results in more accurate like release and storage patterns. And the second one, once we obtain such a model, is very good, useful to do something. Like this is one example. You can see now, these days, we are still in an era that by increasing energy demands, and there are many hydropower dams still are being built or planned globally. And this is from the IEA's sources. And many new dams could further, but meanwhile, that they also could further alterate the hydrological regions and ecosystems, like in these biodiversity regions like Yangtze River and Amazon River. Here, and we see that in the Yangtze River, this is the most one of the most biodiverse regions and river basins. And you can see 3 gorge dams. We know that this is the largest hydropower in the world. And recently, 2 years ago, the second largest hydropower by Hetan and another mega dams are built in the upstream of the 3 gorge dams. So, and interesting, the abrupt hydrological changes followed their full operations. This is a satellite water level, and this gauge reviewed by the satellite altimeters. You can see there is a abrupt hydrological reductions. So, but we know that we don't have operational data for many dams, and nevertheless to say these newly built dams. But timely assessment is crucial, but limited by the lack of operational data. So we aim to provide such a timely assessment using our SPTS. And you can see this is the 3 gorge dams, and this is the 2 mega dams. And we found the downstream locations. Here is after 3 gorge dams, and here is after 2 mega dams. And the red dots means the satellite observations. And we set model experiment we remove these 2 dams, and we can see the effect. So here, this figure illustrates this is a natural baseline, and this is all dam impact. And once removed these 2, this is the 2 dams impact. So we see that during in 2022, later on, it occurred a unprecedented drought, and then we found that during this drought, peak in the summer, it still reduced storing water during the refill stage, because they reduce the downstream water levels, because they are still, the 2 mega dams are still storing water, so they further reduced downstream water levels. And during the winter, and they released water to the downstream, so they increased the water level. That's to say, somehow it elevated the water stress in the dry season. And along the Yangtze River mainstream, this is the mainstream stations, and we quantified that their hydrological alterations in water level, and we found these 2 mega dams upstream reduced high water level and increased water level, and overall they reduced the magnitude reductions across the Yangtze River. And we also further to see in the different climate conditions, and we found no matter how in a wet year and a dry year and a long-term mean, we found their impacts are still significant, and these changes are even comparable to those observed in the 2022 and 2022 drought. And here, we further examined the hydrological alterations in different metrics like flood peak reduction and different percentile flow alterations. And we found that the potential alterations are comparable to the 3 gauge dams. And here is like overall. So you can find the reference here. And we using satellite observations to develop a satellite-based model, SPTS, and this we do a live application, and we can see the rapid assessment for mega dams impacts. So that's all the conclusion.
Okay, thank you very much, Youjiang. So yeah, as you pointed out, maybe satellite is very helpful for rapid assessment, especially for maybe very recently built dams. Okay, so let's move to the next talk. Next one is by Dr. Prakat Modi. The title is Does Spatial Resolution Matter? Effect on Large-Scale Hydrodynamic Simulations. Okay, Prakat, please start presentation when it's ready. And everybody, because of time, please let's have a discussion on Zoom chat. Okay.
So am I audible?
Yes, you can start.
Okay. Hello everyone. I am Prakat, and I will be talking about like does spatial resolution matters, especially in case of like large scale hydrodynamic model simulations, and if it matters, like where and why. So coming to the introduction, so usually the assumption is that like high resolution will provide better flood predictions, and some of the previous studies shows that that the improvement in the discharge evaluation due to high resolutions are it can be better flood plague flow for smaller rivers due to increase in the resolution. But at the same time, few of the researchers like Arts et al. 2022, they showed like coarser resolution can obtain like similar results to the high resolutions. So there was a mixed outcome, both notable and negligible enhancement attributed to the increased spatial resolutions. And these previous researches have some limitations and some challenges. So one of the things is like most of these researchers focused on discharge, and so they missed like few of the important variables like the river depth, water surface elevation, and flood extent, maybe due to the limitations of the data availability or model limitations. Also, when you compare with the observations, they have like biases or errors which can affect the results. Also, you need to calibrate models and optimize them, so it's challenging. And along with that, like most of these previous research I focused on like whether the model is performing good or bad due to the impact of resolutions, but what's the reason behind the mechanism behind like how they are happening is not so clear. So we needed a better framework for like comparison and to further improve the model like development. So to overcome these limitations and to improve our understanding about like how resolution will impact, we compared the CaMa-Flood simulation at various resolutions without considering the observations. So we neglect the error from the observations. And since we are considering only the model simulations, we consider like the same runoff forcing, same river channel parameters for the CaMa-Flood simulations for different resolutions. We consider like 1 minute, 3 minutes, 6 minutes, and 15-minute resolutions. And we consider like different variables like discharge, water depth, total flooded area, and flood extent patterns, and compare them to know like how the spatial resolution is affecting it. So first of all, like to compare the discharge and water depths, which are like point observations, we defined the virtual gauge based on like lowest resolutions, and then again allocated the high resolution based on it. So we only compared the mainstream river channel for the Amazon and then the substream joining the mainstreams. And using that, we got like 1198 virtual stations. Since the flooded area and flood extents are like not the point observations, we can't compare them using like the directly. So we defined the different zones based on like the scale of the river, like mainstream or substreams, into like 5 different zones and compare like total flooded area and flood extent for those zones. First of all, like the overall result, and what we found is like we compare like the different resolutions and keeping the high resolution as the baseline. And we found when we compared, we found very good like R square values for both discharge and the river water depth. And we can see like we can go like as high as like 0.9 R square. So the phase is very good in different resolution have like very good in phase. Also for discharge, we found like the R square can go like 0.8 for like more than 80% of the locations. And whereas the river water depth can go like 0.6 0.64 here, and it shows like maybe river water depth is more sensitive to the local parameters and can have some impact on, like, small changes can have like larger impact on the their performance. But the second thing is like we identify, like, when we see the spatial distribution of normalized NSC and R square for discharge in water surface elevation, what we found is like large dissociation for discharge was mainly occurring at the river junctions in the mainstream, or when the substream is joining like some larger or smaller further substreams. Whereas the large dissociation for water depths occurred mainly on the upstream or headwaters. So this shows, like, since the CaMa-Flood uses like subgrid parameter from high resolutions, these are not happening because of the parameterization, because these two differences are occurring at the different places. But then what are the reasons behind these dissociations at the few of the places? And we identify like the back performance are the large discrepancies between the performance due to the resolutions, and we consider like where the normalized NSC value is less than 0.3. We found like 2 to 3% of the locations. We can see like 36, 37 locations here, and then 28 locations for like discharge. And there were like mainly three things for the discharge, like bifurcation, backwater, floodplain conveyance, and for river water depth, bottleneck sections causes the large dissociations. And how these are impacting, I will go through them one by one. So first of all, like a large dissociation, the discharge mainly occurs due to the river bifurcation scheme. So what happens, due to the various resolutions, physical properties of these bifurcation channels have like different properties, such as like channel length or gradient. And because of this, the bifurcation flow is like different in different resolutions. So here we can see, like, when we do the simulations without bifurcation, we got almost similar or same discharge at the virtual stations. But when we activated the bifurcation scheme, we got like different total like discharge. Then the second one is like the floodplain conveyance. So what happens is, like, CaMa uses the assumption of uniform subgrid cross-section topography, and then when in low resolution, when a smaller unit catchment combined with the like the mainstream, like here, the floodplain is usually much higher, and this causes like larger floodplain flow conveyance. So we can see like for the same river water depth, the discharge for the different resolutions have like similar like the channel discharge. But what we found is like the floodplain discharge for the same river water depth, as the resolution increases, it increases. So the lower resolution might have like this kind of, like, in very flat terrain, might have like much higher floodplain flow conveyance and causes like some dissociations. The third one is like backwater effect. So we know like CaMa-Flood uses like unit catchment and unit catchment outlets. So because of the relative locations of these unit catchment outlets, it can have some the impact of backwater effect. So in high resolution, these unit catchment outlets are like much closer, and since whereas for the low resolutions, it have much farther away. So the chances of like having the backwater effect in the high resolution increases because of this. We can see like large hysteresis for 1 minute, but the blue one is like less hysteresis and like less backwater effect. So these kind of discrepancies can happen. Coming to the river water depth. So what happens is, like, when we consider like the high resolutions, it can capture the changes, more variability in the river channel width. So we can see like the high resolution can capture this kind of like very narrow channels, and whereas the low resolutions can't capture it. So because of this, like the bottom channel sections, there's a flow, like interruption in the flow, and then increase in the like the water storage or water depth and the upstream side, and this will cause the increase in the water level. So here we can see like the increase in the mean water surface elevations when there is a narrow channel sections happens for the high resolutions. These things doesn't present in the low resolutions simulations. And then next to come to like total flooded area. So we compare like the different zones, 1, 2, 3, 4, 5 here we can see. And then usually the high resolutions have higher flooded area because more small tributaries are resolved in high resolutions and then have like more flooded area. Also, like the in the high resolutions, many bottleneck channel sections can cause the increase in the water level, and then again, it will cause the increase in the flooded area. We also found like when we compared the flood extent, what we found is like for the larger rivers, like here we can see the critical success index was very much high, like 0.88 or 0.91, whereas for like smaller streams, it was like it reduced to like 0.54 or 0.38. This is mainly because like smaller channel sections, there is a limitation in downscaling schemes. Also, we can't represent the smaller streams in these for the low resolution simulations, and also the backwater effect, which I earlier like discussed. So these can have like the decrease in the comparison between the flood extents. So this was all about it. So main conclusion is like CaMa-Flood can perform like simulations at various variables at low resolutions as good as high resolutions, but there might be some discrepancies because of few of the model physics changes due to the spatial resolutions. But medium resolutions like 6 arc-minute might be like adequate for most of the global studies. And further improvement in hydrography data or downscaling method can increase our like the capability of model to perform much better in the future. That's it from my side. Thank you. If you have like any question or comment, you can email me or like ask directly.
Okay. Oh, thank you very much, Prakat. So yeah, it's good to see the resolution dependence is not so large, but when we have a difference, there is a physics-based reasons. Okay. So I'd like to move to next presenter, but unfortunately, Ruijie Jiang cannot join tonight, so I have his video. So let me play his presentation.
Our recent work about the analysis. Hello everyone, I'm Ruijie Jiang, and I'm now the postdoctor at Tsinghua University. Thanks for Professor Dai for giving me this opportunity to introduce our research. Today I will show our recent work about the analysis and comparison of the flood simulations with the CaMa-Flood model at different spatial resolutions in the US. Floods are among the most frequent natural disasters around the world, posing serious risks to both human life and socio-economic development. Global hydrodynamic models such as CaMa-Flood play a crucial role in the large-scale flood simulations. By accounting for the inundation processes in flood plains, CaMa-Flood can achieve improved simulation results for flood peak flow than the native routing schemes of the hydrologic model. Flood management places high demands on the accuracy and resolution of flood simulations. With recent improvements in computational resources, the availability of high-precision topographic data, and the development of high-resolution runoff data, fine-resolution flood simulation has become possible. However, utilizing fine-resolution models also means consuming more computing resources. The balancing model efficiency and accuracy remains a significant challenge. The first thing to acknowledge is that the fine-resolution models may contain more details of the river network, and the low-resolution model cannot represent the upstream drainage areas of small reaches accurately. However, a fine-resolution model does not necessarily result in a more accurate simulation of river discharge, particularly floods. Therefore, the optimal level of model resolution at which the river network can be represented well and the floods can be simulated well remains to be studied. In this study, the forcing data we used is the 5-kilometer resolution runoff data developed by Yang, which was generated by the peak hydrologic model. This runoff dataset has also been widely used for flood simulations. The runoff data was used to force the CaMa-Flood model to simulate daily discharge in the US from 1990 to 2009. The temporal resolution is daily. We have run the CaMa-Flood at these four resolutions. We mainly focus on the upstream drainage area, daily discharge, flood peak flow, and flood timing. We first classify the relative area of the upstream drainage areas in the CaMa-Flood model according to the observed upstream drainage areas. The results show that for the large reaches, that is the observed upstream drainage areas greater than 2,500 square kilometers, the relative area of the upstream drainage areas for most stations at all resolutions was within 20%. The differences in the upstream drainage areas among the various resolutions were primarily observed in smaller reaches. Additionally, the upstream drainage areas in the low-resolution river network was generally larger than those in the fine-resolution network. In discharge and flood simulation, most of current research consider a relative area of 20% or less in the upstream drainage area as an accurate representation of the upstream river network. As shown in this figure, the CaMa-Flood model with a resolution of 5 km, 8 km, 10 km, and 25 km resolution is capable of accurately representing the upstream drainage areas for reaches with an upstream drainage area larger than 100, 300, 500, and 2,500 square kilometers. The areas of 1, 5 km, 8 km, 10 km, and 25 km resolution grade are nearly 25, 70, 100, and 625 square kilometers. Therefore, for the accurate representation of river network, a resolution can be selected if the target watershed can be represented by more than 4 grades of that resolution. We have then compared the KGE of the daily discharge simulated by CaMa-Flood at different resolutions. It's evident that as the resolution increases, the simulated daily discharge becomes more accurate. The daily discharge simulated by the 25 km resolution CaMa-Flood is worse than that of the other 3 resolutions. We have further compared the flood peak flow simulated at different resolutions by CaMa-Flood. It can be seen that for most of the stations, the flood peak flow was underestimated by CaMa-Flood at different resolutions. This is mainly because that the extreme precipitation is underestimated and is a widespread shortcoming in current flood simulation. Despite this, the 5 km resolution CaMa-Flood performs best in simulating flood peak flow among all the resolutions. Specifically, the substantial overestimation of the flood peak flow by the low-resolution CaMa-Flood model is corrected in many stations through the use of high-resolution model. This is mainly because the low-resolution CaMa-Flood has overestimated the upstream drainage areas in many regions. Here we used the timing of the annual maximum daily discharge to represent flood timing. Different from the daily discharge and the flood peak flow, the timing of the flood peak flow simulated and different resolutions by CaMa-Flood is comparable at most of the stations in US. We also categorized the relative area in annual maximum discharge simulated by CaMa-Flood at different resolutions by observed upstream drainage area. We found that the differences in the annual maximum discharge simulated at different resolutions are concentrated in the stations with a small upstream drainage area. For the river reaches with upstream drainage areas less than 100 square kilometers, the 5 km resolution CaMa-Flood performs best in simulating flood peak flow. For the river reaches with upstream drainage areas larger than 100 square kilometers, the flood peak flow simulated by the 5, 8, and 10 km resolution CaMa-Flood are comparable. For the river reaches with upstream drainage areas larger than 500 square kilometers, the flood peak flow simulated and different resolutions by CaMa-Flood are comparable. This suggests that improvements in the representation of the river network do not necessarily translate to better simulations of annual maximum discharge. One of the reasons is the uncertainty of river channel parameter. For example, in this station, if the channel cross-sectional areas in the 0.1 degree and 0.25 degree CaMa-Flood are identical, the improved upstream drainage area can lead to the improved flood peak flow at this station when using the 10 km resolution CaMa-Flood compared to the 25 km resolution. And this is the conclusion. Firstly, for accurate representation of the river network, the selected resolution should allow for the target watershed to be represented by more than 4 grid cells at that resolution. On this basis, for rivers with upstream drainage areas larger than 500 square kilometers, if high precision river channel parameters are unavailable, employing the 10 km resolution model can save computational resources and can still achieve flood simulation results comparable to those of a high resolution routine model. And that's all. Thank you very much.
Okay. Oh, thank you, Ruijie. Oh, I think it's good to have a kind of a similar agreement to Prakat result. And but for sure, for smaller river basin, we need a high resolutions. Okay, I'd like to move next presentation, and the next one is by Dr. Fitzmu Meskel from Australia. So Fitzmu, could you please share your screen and start presentation?
I hope you can hear me now.
Oh, yes, I can hear you.
I'm trying to share my screen. Sorry, can you see my screen now? Or?
Oh, yes, I can see your screen. Oh,
But the slides is not coming, yeah?
Yeah, it's editing mode, so you'd better to switch to presenting mode. Okay.
Okay. Thanks. Sorry about that. So yeah, Fitzgerald Lemeskel from the Bureau of Meteorology. I'm going to talk about the recent paper that we have published in Hydrological Sciences. It's focusing on assessment of JULES land surface model coupled with CaMa-Flood for an operational streamflow forecasting in Australia. Yeah, it's co-authored by several people from the Bureau internally, as well as the University of Tokyo, CH, ECMWF, and Met Office. So it's really a collaboration of several people. Just to give a context, so at the Bureau of Meteorology, I work in the land modeling team, and we are looking at enhancing the JULES land surface model for using for hydrological applications. And yeah, part of that work involves in looking into the vegetation component, the soil physics, and also the hydrology in JULES. And particularly, I'm looking at the river routing and trying to use CaMa-Flood into the JULES land surface model. So this paper is part of that bigger project. And the benefit of this work is there are twofold. One is really we are by using JULES and CaMa-Flood, we are much more closer into the air system model, and this allows us to do the closing the water balance and energy balance. And it also, on the other hand, allows more consistent and seamless hydrological forecasting. So the aim of this paper were threefold. One is to try implement CaMa-Flood to simulate Streamflow and look into evaluate the performance. Another important part of this work was really how well CaMa-Flood and also JULES perform for Australian conditions. CaMa-Flood has been tested in various regions globally, but not much of work has been done in Australia. So this is one of the first. Maybe there are others, but that are looking into CaMa-Flood for Australian catchments. And we also did benchmark that across with other land surface, other models, mainly the ORAL water balance model, which is currently operational for the Bureau service, and as well as the two reanalysis datasets, BAR-R2 and ERA5 LAN. Here is the workflow I'm using, very straightforward. We use input from land surface model, runoff inputs from multiple land surface model. I'll show those models in the next slide. Applying to CaMa-Flood, take out the Streamflow, I focused only on the Streamflow output on this paper, and following the grid to gauge allocation, we extract Streamflow for catchments and evaluate against observed Streamflow. So this is a list of models considered and characteristics. So they are not all exactly the same forcing, some or spatial scale. They could be different, but all of them have been routed at the same spatial resolution, which is about 5 kilometer resolution. And this is where I tested the outputs. So I took more than 460 catchments. So all those dot points are showing the catchments. And the catchments have been classified into 3 groups, perennial, intermittent, and ephemeral, really to understand the performance of the models for these particular catchments. And also we can see some of the catchments that have identified for some case studies. I'll show some of the results for those specific results for those catchments. Moving into some results. So this is one of the representative results in the paper. So what I'm showing here is basically for perennial, intermittent, and ephemeral catchments. I also grouped the perennial and intermittent catchments into all flows and high flows and low flows. But I haven't tried for ephemeral flows, ephemeral catchments, because most of them are already dry or zero. So we have KG and bias results, and what you can see is essentially perennial catchments generally perform better. The models perform better, which is not surprising. And on the other hand, for ephemeral catchments, performance across all the models is relatively low. We can see the top 3 models in this case are the JULES and the ORA, as well as the ERA5 LAN. Particularly the ERA5 LAN is good in the low flow case, but it diminishes or reduces scale is a little bit lower for high flow. So yeah, main point here is really ephemeral catchments are relatively low scale, and And we do have a lot of them in Australia, so that's why it's very important to really benchmark or any comparisons. When we do that, we need to look into these catchments separately and try to improve the model for these catchments. And another point, when I look at the compare runoff outputs before actually doing any routing, is the runoff outputs can also be significantly different, even though in some cases with using the same forcing. So what I've compared here is the middle one here, or the second one is the Aura L, which is I use the main benchmark. When I compare that with the others, we can see there's the JULES one is much wetter in this area and also relatively drier here. These two, third is also uses really JULES as land surface model, and I can see similar pattern there. On the other hand, Era 5 land has more dry, for example, in this part, and also in the Southeast Australia. So this is very important because, yeah, before even doing any river routing, there's some big difference between the models in the runoff. And one interesting, I've looked at several of catchments more detail, but this catchment seemed very interesting. It is Gascoyne River, and I took an event in 2018, some significant event. What I have looked at here is I just took two of the models, JULES and Aura-L. Both of them are forced with the same rainfall, called this is AGCD rainfall, and we see very big difference in the runoff output, and that also translates into the stream flow. And I was trying to understand why is this happening. So we can see here a plot of the rainfall, and I looked at the soil moisture and the flow, and what I can see is immediately in case of the Aura, the soil moisture really increases rapidly once on the onset of rainfall compared to the JULES one. So which tells me that most of the rain in case of the Aura is infiltrated into the soil compared to the JULES model. So that could be one interpretation, and I haven't looked much more detail than some of the parameters and the hydraulic conductivity that there may be more information there. But yeah, this is something we can really look into by using CaMa-Flood to understand how the models perform. I looked at sensitivity analysis as well, particularly looking into the CaMa-Flood parameters, the river width, depth, and Manning's coefficient. These are those main three parameters I looked at, and yeah, we can see there's some sensitivity in some of the catchments, particularly in the first one, the Burnett catchment. So when I change the parameters a little bit, I get a much better fit for this hydrograph. But in case of Catherine River, that improvement doesn't seem, already the model is performing really well, but doesn't seem that significant sensitivity. So yeah, I'll invite you to read more details on the paper. Because of it's no time, I'll stop here. Thank you.
Okay, thank you very much, Fitzum. Yeah, obviously dry land hydrology is our next target. And yeah, Australia is a good example. Okay, so I'd like to move to the last presentation by Shudon Zhou. Yeah, yeah, Shudon, please start your talk.
Okay, yeah, you can hear me. Right. So thanks everyone. Today I will present the paper which published exactly last year. So the title is Benchmark Framework for Global River Models, published in Journal of Advances in Modeling Earth system. And this paper has also been selected as the research highlight. And the work was done when I was in Tokyo with the support from Yamazaki Sensei and many other colleagues. So the benchmarking is worked for actually compare models between among models. As we see from today's presentation, we have many kinds of different developments in the last decades. For instance, the bifurcation, dynamic seawater levels, dam operation, and also the latest levee model, and the computational accelerating by different methods. And also we need to have the calibration, which will need a lot of simulations. So in this case of large demanding of the running CaMa-Flood and assess the performance of the model, we need to do the benchmark. But when we do the benchmark, one of the limitations is that the current data, observation data, is limited in space and also in time, especially the river discharge. And then the river dynamics, which in addition to the river discharge, the water level and the inundation area is also to be further evaluated. So so we need to do the benchmark. But what is the benchmark? According to the dictionary, the benchmark is the act of measuring the quality of something by comparing it with something else of accepted standard. So we need to have a standard benchmark CaMa-Flood, and then at this benchmark point, we can compare different developments from it. So the work we are working is we aim to build a benchmark system that is which can automatically and also user-friendly, extendable to evaluate model performance against multiple observational variables with varying scales. So the benchmarking can be divided into 3 steps. The first step is to preparing the simulations and observations to convert them to the same format to be compared. And the second step is to develop some model assessments methodology, including the metrics, also the model comparison metrics. And the third step is to visualize the result in the easy way. So first, the data, and we usually use the river discharge data, but we know that the discharge is limited by the space and time. So we include more data about the water level and the water's surface. And then the red part is the metrics and visualization and web application. So for the data, we included the altimetry data, which is developed from HydroWeb. We can see from this graph, the HydroWeb is, or the water level data is distributed all the world, and the space coverage is much more than the river discharge. And we can take a snap at the water level, how this can be used to do the model validation. For instance, there is one visual station. We can see although the time interval of the water level is large, but it can follow the hydrograph very nicely. And this has a seasonal variation, but for this station, they are weak in the seasonal variation, but we can see the general trend of the hydrograph is observed, is captured. But for the maybe rivers with low river discharge, maybe the water level is not that perfect. And also for instance, for this one, the flow peak is much higher than the general river discharge. The water level cannot be very good compared to the river discharge. But at most of the large rivers, maybe water level is a good proxy to evaluate the river discharge. And then for the water surface area, we know that water surface area is distributed everywhere in the world. For instance, we can see from this large round that water surface area should be used as one of the good comparable variable to evaluate the model. But before using the different kind of data, we have to do some pre-processing. For instance, for the river discharge, we have to allocate them to a proper location compared to the river, compared to the model settings, and the details can be like can be reached in the paper. And this is for river discharge. For the water station, it's the same. It's the same. And then for the flow plane mask, that is the water surface area, we also published one paper that you can refer to. And then we develop a different matrix. Actually, this is a collection of different matrices, including the bias, the correlation, the NSE, KGE. So with all these metrics together, we can evaluate the model in the more overall way. And also we have developed the comparison metrics. We use 3 different kinds of metrics to compare which model is better. And then for the visualization, we have developed a very simple the graph. Okay, from the most left one is the baseline, and the right part is the model which is to be compared. If the color is blue, then the model is better than the benchmark, and if the color is red, the model is worse than the benchmark. So in the framework, we can have many different kinds of model settings to be compared in the model chain. For instance, the CaMa-Flood model chain, including the atmospheric forcing and the runoff generation, also the river routing, which is the CaMa-Flood itself. So we can compare any of the parts in the chain. And then we have some models, some examples. In the paper, we showcase the model forcing difference between the baseline is the Earth to observe, ECMWF, and the two compared model is driven by ERA5 and weak bias corrected. So we can see compared to the benchmark, the weak bias corrected model is much better than the 2 because we see more blue colors here. And this also in the framework we can showcase the how the models are compared in the space. For instance, here the blue color shows the model is much better, and the red color shows model is worse. And then if we compare M2 is the weak bias corrected to the benchmark, we can see most of the dots are blue, means model is better. So we can also, that was for river discharge. Then we can also compare the water surface elevation and also the water surface area. We can see the elevation and the area is showing different trend from the river discharge. But for the water surface area, maybe the third one, that the weak bias corrected, is still better than the benchmark. But that is not the case for the water surface area. So we still have a lot of work to do, even though we have calibrated the river discharge in a good way, but the water surface area and the elevation should be one of the points that we have to still improve. And these are the some examples of 2 cases. This one is for doing the model parameters. And the default parameter is actually, after comparison, the default parameter is actually still the good one. So even we change the parameters of the river channel depths, the model is getting worse. And here we compared the weak bias corrected compared to the model driven by GLOFASS. Actually, GLOFASS is not that good compared to the weak bias corrected driving CaMa-Flood. And also we compared to those river discharge driven by the machine learning result. Actually, the machine learning result is still kind of better but they use a lot of data, so that's reasonable. But for the benchmarking, we know that it's still not developed in the final way. Actually, for instance, for other benchmarking system, they have developed like decades until the last version. So we still have a lot of work to do until to the last step. So what we want to do is to invite you to join and contribute to the benchmark system. And if you can provide some result for our benchmark, that is very welcome. So yeah, that is my presentation.
Okay. Oh, thank you very much. So I put a message in chat about, I think every year we have to benchmark the latest version of CaMa-Flood to confirm how much the accuracy is improved in 1 year. So this is currently in annual meeting. So let's do it from next year.
Yeah. Okay.
Okay. And I'm happy if everybody can join this benchmarking activity. Okay.